Hello, everyone. My name is Cong Minh Khang of Group 11. And before we get into our face recognition AI presentation today, I'd like to ask you a question. How long do you think you'd take to recognize my face in a crowd like this? 10 seconds? 20 seconds? A minute? The truth is that it would be very difficult, even if you were actively looking out for me. Now, such capabilities to recognize faces in a crowd was sorely needed in a 2016 terrorist attack in Germany, where a man crashed a truck into the market and then fled the country. He was able to flee even though he were under great investigation already, and even appearing in CCTV camera footage 2 days after the attack. The thing is, police were busy capturing and interrogating the wrong man because of eyewitnesses at the crime scene were confused and mistakenly catch the wrong man. Now, this incident highlights how unreliable humans are at recognizing and identifying faces and raises the need for a machine to be able to do that to ensure public safety and security. Now, traditionally, systems like these are done using convolutional math on matrices, which has a lot of downsides. Number one is that it has very low accuracy. And if the target were wearing face mask or a hat, or if the target were looking a different way or was in a different lighting environment, the accuracy of the recognition would go down dramatically. Another thing is that the system would need an expert in computer vision to design and implement, which means it's very difficult to adopt widely. Lastly, in order to add faces to the database of faces you want to track, you would need to record and store a lot of data, which means it is not easy to scale up. Now, our system will need to address all of the above problems and also do more, like ensuring high speed so it can handle the throughput of people in the crowd and ethical handling of the data it collects on the people. If we implement this using modern day AI technology, we can do all that, and it should look something like this, where an AI will watch a video feed and then correctly identify the faces and name them out for the user to see.
Hello, my name is Ngo Phan Khai Tu, and next I will introduce you about the system pipeline. The system pipeline contains six main steps and divided into four main stages. The first one is input or test the face. The second one is pre-processing the face input, containing face and landmarks detection and face alignment steps. The recognition stage contains feature extraction and feature matching using face gallery, and then we have the output of face verification and identification. So what is the face detection? The face detection is the first step of using AI to detect and recognize the faces in a picture. The face detection mainly focus on where are the faces and how many of them in the frame, rather than recognize who they are. Uh, One technique we use to uh, detect the face and then recognize them is MTCNN, stand for the Multitask Cascaded Convolutional Networks. This is the project of authors Kai-Peng Zhang, Dapeng Zhang, Zifeng Li, and Hu Chao. The MTCNN contains three basic structures. The first one called the first state or the PNet. The PNet will transfer the text image into the image pyramid and then using the bounding box regressions to determine the areas which have highly percentage of containing the face. Then we move on to the next step we call the RNet. This step will use the NMS to clean up all the abandoned bounding box and keep as less uh, bounding box as possible. And then in the final state or the ONet, the NMS will be used one more time to keep only one bounding box and start to recognize five facial landmarks for the further recognition. In comparison of MTCNN versus others, we can see that although the MTCNN is not the best option in AP at 0.5, however, it only contains three basic structures so that it can contain uh, it will require less resources than the others, which can be used on small devices like the mobile phones. However, it's still have the basic technique to recognize face effectively. For example, in the next part, I will show you three basic difficulties facing when using face detection and recognition. However, these are also easily by the MTCNN. The first one The first one is the pose. The pose is the faces when uh, using face mask or sunglasses. So this will make the AI harder to recognize the face. Next up is the light, which is quite likely to the pose. The light will affect a lot of in face recognition in some case like this on the slide. And the last one is emotion. The emotion sometimes create makes confuse in face recognition or face detection. And the scale is also the main effect to the way the AI recognize the faces. In some case, we will be confused uh, by detecting a lot of faces and abundant faces on in the image. So that is the end of my part. Thank you for listening.
So, hello everyone, I am Ankit, and to have just shown how MTCNN detects and aligns every face in image and video streams. Now, my part will explain how we take those aligned face graph and answer the question whose face is it using FaceNet. So, before we diving into FaceNet, let's clarify what we mean by face recognition and review its two-man mode. The face recognition is the process of we want to identify a person or people in an image or video. And there will be two approaches. The first approach is the face verification. So we want to compare exactly two faces and ask the question, is this the person who they claim to be? A very common example is unlocking the smartphone with a face ID. And in this approach, we want to maximize the speed to enhance the user experience more than the accuracy or robustness. Next is the face identification, which is the one-to-many searching. You will compare one face against a gallery of thousands of faces and ask which identity in our database match with this face. So for this approach, it is used more for the security cameras or access control in the large facilities, and the accuracy and the robustness in this case are more matter than the speed, as we're going to capture the image from a wider angle, so the accuracy will likely to be affected by light, pose, or maybe other factors. So therefore, the consequence of missing one match would cost more than taking a few extra milliseconds or a second. So next, let's me introduce you guys about the FaceNet, which is introduced in 2015 by the Google researchers. FaceNet will use the deep learning to extract the facial features, and it will represent in the each face in the embedding space as a compact 128 dimensional vector. Then finally, it will train using the triplet loss, which and for those embeddings that are the same will be pulled closer, while the different one will be pushed apart. So let's see how the embedding vector work. The embedding is how we going to use the technique to convert a high dimensional, usually a sparse vector, into a lower, usually a dense vector. So in the image, we can see that the point of the same person will be clustered tightly together, while those that are different will be enough far apart. Next, after we turn the face into embedding vector and represent it in the embedding space, uh, we want to recognize the person in different conditions. So we want to use a triplet loss function for training the model to be more flexible. So the triplet loss will allow the FaceNet to train three faces at the same time. There will be the anchor, the positive, which is labeled the same with the anchor, and the negative, which is different to the anchor. So then it will use the mechanisms of push and pull to reduce the distance of the same face and increase the distance between different faces. Next, let's answer the question why we want to choose FaceNet, but not the other. So I make a comparison of the FaceNet to other different models that I found are ArcFace and CosFace. These two models use the same technique, but it will use 512 dimensions, which is four times larger than the FaceNet. And as you can see, the LFW accuracy in the top far equal to zero point 0.1 of the three models are likely to be the same. However, we can see that FaceNet have a lower inference time and the lower in model size which outperform the two other models. This make the model ideal for the large scale identification when you want to process thousands of faces in real time without excessive storage or compute demands. So this is the end of my section. Thank you for listening. In fact, we'll now continue our presentation with the privacy, bias, and ethics considerations.
So now, moving away from the purely technical aspects, it is absolutely crucial that we dedicate the time to discuss the privacy and ethics. Facial recognition technology, as powerful and beneficial as it can be, carries significant ethical considerations and potential risk to privacy. On the slide, we see a headline: How China used facial recognition to control human behavior, and the accompanying text from an Alfred Nguyen CNET article, Stock Big Ones. When facial recognition is everywhere, anything you do is fair game for public shaming and punishment. Serve as a potent reminder of the societal impact these technologies can have. As engineers, researchers, and developers, we have a profound responsibility to approach this field with caution and a strong ethical compass. We must constantly ask ourselves, how is this technology being deployed? What is the safeguards against misuse? How are we protecting individual data from ensuring content, from ensuring and consume? And censoring content about what are the potential biases in our algorithms and data sets, and how can we mitigate them? These aren't easy questions, of course, but they are essential to address to ensure that facial recognition is developed and used in a way that respects human rights and dignity. This is an ongoing conversation that must parallel technological advancement. We move on to the next slide here. All right, before we move on to our final conclusion, let's have a quick recap of the main components of the AI model we've been discussing. On the left side of the slide, you can see the stages of MTCNN, the multitask cascade evolution networks as we discussed before. Stage 1, PNET. This is a proportional network which quickly generates candidate facial windows. Stage 2, RNet. The refined network further filters these candidates and refines the bounding box. Stage 3, the ONet. The output network gives us define or precise bounding boxes and also detect key facial landmarks. This cascade approach ensures both at speed and accuracy in detecting faces within the image. Then on the right, we have a conceptual representation of a triplet loss function, which is central to FaceNet. The goal here is to learn an embedding space where distances correspond to facial similarity, which I can anchor image, a positive image of the same person, and a negative image, different persons. And the loss function works to ensure that the distance between the anchor and the positive of the AP is small, and the distance between the anchor and the negative of the AN is large by at least a certain margin. And critically, a slight note at the bottom, the emphasis shifts based on the application. And for verification, for example, unlocking your phone, a one-for-one match, speed is often prioritized for smooth user experience. And for identification, for example, finding a person in the database, 1/n match, accuracy is paramount for security. And that brings us to our conclusion. Well, we'll summarize our findings and offer our final recommendation. FaceNet plus MTCNN. Our analysis shows that the combination of MTCNN for face detection and FaceNet for recognition is best suited for one-over-n applications. It also performs admirably for one-to-one verification. This package is versatile and powerful pairing. For the trade-off consideration, it is important to acknowledge that no single solution is perfect for every scenario. For purely verification tasks, considering mobile optimized variants might offer better on-device performance if extreme accuracy is an absolute top priority. Conversely, for ultra-large galleries requiring maximum accuracy, arc-face or cross-face may be preferable. But this might often come at an increased competition cost and order size. And for the final recommendation, taking these points into account, our final recommendation is as follows. In most cameras or enterprise deployment, the gallery size are in the 10,000 to 100,000 range, and real-time performance is matters. Then MTCNN plus FaceNet provides the best balance of power, accuracy, and robustness. This combination hits a sweet spot for many practical, real-world applications where you need reliable performance without requiring supercomputer resources for every lookup. And that brings us to the end of the presentation. On behalf of the team, I'd like to say thank you for your attention. We hope this has been informative, and we'll be happy to take any kind of question that we may have. Thank you for listening, and goodbye.